Let me just tell you what I'm planning on doing. I'm going to cover some problems. I got asked a question about, I think it's 59. Am I right about that? Who asked that question?
I think it was 58.
58. It's the one with the current density, right? I worked at my office with, what? You were there. Who else? You guys. I'm going to do it on the board. I want to go through. Then I'm going to go through and talk about magnetic circuits. Now, be careful about. I want to make sure you see this. Some of you have had this in power, I think. And then, after we do magnetic circuits, I'll go through the boundary conditions that are, you'll find out are very easy to understand the reason for it and why. And after we wrap this up, I don't know if we'll get done today, we'll head into chapter 5, okay? All right. All right, so first that problem, if you've got, did I do something? It doesn't matter really, I don't think. Go ahead, just give me the specifics. They have a wire, right? So I'm just going to do the cross section. Wire has radius A and there's a current density in it. And the current density, can you tell me what that is? Something times rho. I forgot exactly what it was. Anybody? You asked me about, I mean, do you remember what the constant is? It's like 6 or something, I don't remember.
Oh, it's 4 rho.
4? All right, so it's 4 rho, and it's in the A rho direction, right? Is it amps per meter squared? Nope.
It's amps per centimeter squared.
Oh. Flipper. All right, I'll tell you what. We're going to make it amps per meter squared by multiplying by 100 squared. That would be 4. Y'all follow me on this class? So we're going to do it this way. So this is going to be really 40 times 10 to the third amps per meter squared. I get to call the shots on this. All right, you with me on this class? Yes.
Is this 5, 9, or 5, 8?
I don't know.
That's by China.
Oh, do you want 5.8 or 5.9?
I mean, it doesn't matter. I asked you.
We'll do 5.
In the email.
I'll tell you what, we'll do 5.8 and 5.9. Let's do 5.9 first, then I'll go back and do 5.8 since I got it on board. Everybody okay with that? Now, if you follow this, what they want is the magnetic energy, and I think the inductance in terms. Yes? It has to be rho, right? Isn't it times rho? I'm making it a function of rho on purpose, isn't it?
It's 4 rho.
All right, and here's, I believe they ask for magnetic energy and then inductance. Is that correct per meter? Internal? Just tell me what they
It
ask.
says find the internal inductance per unit length of the wire for this current.
All right, this is a good problem. Again, this is a good problem. Now, I hope we got your attention. Here's what I want you to think about. How do you get inductance? Well, there are 2 ways. You can have the flux coupled in a circuit, right, from one circuit to the other and divide by the current causing it, or you can find the magnetic energy density, then integrate that over the volume that you want the total energy in. You get the total magnetic energy, and that has to be equal to 1/2 Li squared. Y'all follow me? There are 2 ways. We're going to do it the latter. So from this, J, what we need now is going to get the H field. Y'all follow me on this? We have to have the H field to get the magnetic energy density. So to get the H field, how would you get it? Now this is like a problem we've done before. What would you do? How about Ampere's law? Y'all with me, class? Everybody understand that? If we use Ampere's law for this, what happens? We're going to say we need the H field. We're going to assume it's cylindrically symmetric. I hope you all see this. This is the Z-axis coming out of the board. This marker, I'm not going to hit you, Corinne. Don't worry. Just going to throw it there so I get rid of that thing. And this guy's seen better days too, I think. Yep. We'll find something that works good. And this one. We'll go with this. So we come out at distance rho, and now I'm going to draw a circular path, and I know, let's see, if it's the current's coming out of the board, then this would be the direction of the H field, But I know that the H field as a function of rho is only in the phi direction because of arguments of symmetry. Is everybody all right with that? Then I'm going to state explicitly Ampere's law, the integral of H dot dl around the closed contour is equal to the integral of J dot ds over the surface. Everybody follow? I'm just putting it down so everybody understands where I'm getting the next step. So over here, what is this always going to be? Without me writing anything more. People, circumference of the circular path, right, times the H field. You all follow me? Give me a show of hands if you do. I know you had it tested. So it's going to be 2 pi rho. Does everybody understand that's the circumference of the perimeter times H phi. And that will be a function of rho, but I'm just going to leave it like that. That's equal to the current enclosed. How do you get the total amount of current flowing? When I say that, I'm saying that all the current that is inside or penetrating this surface normally, that's what I want. Y'all follow me? So first you put the current density in. That's the current density. How about I do this? I'm going to call A 40 times 10 to the third. Just leave that alone. And I'll make this just A. That way I don't have to keep on writing that. Everybody with me on this class? So over, actually, maybe not A, because A's, how about we make it K? Something, it's K times rho. K is that. Just to make things easy to keep track of. So I come over here and I put down first, I have K times rho, A rho, has to be dotted in with a differential unit of surface. What's the differential surface here, class? It's going to be what? In this direction it's d rho, isn't it? And in this direction it is rho d phi. Can everybody follow me on that? That's the white drawing. I'm going to see this right here. Can you all see it in the back? With me? All right. So this is going to be dotted in, and it's going to be d rho times rho d phi. What direction is it? A rho. It has to be normal to the actual surface, the differential surface. Y'all look at the unit vector has to be normal. Now, where does the integral go from? Where d rho would go from where to where? Be careful on this one. From 0 to rho. Correct, class? Because remember, the radius, we're not outside it at A, we're only out to the point rho. Do y'all follow me? With me on this, guys? Okay. So this goes from 0 to rho. What about phi? Anybody? 0 to 2 pi. Now, technically, I should prime this stuff because you can't integrate and end up on something that's a function of kernel of integration, anything inside. But it doesn't really matter. I'm an engineer. I know it's a dummy variable. It's going to be integrated out. A rho dot A rho is 1, so get rid of that. Now go through the integration. First, the 2 pi just comes out as 2 pi, right, when you do d phi? Now, what do you have here? The k comes out, right? And I have rho times rho, or rho squared d rho, or rho, when we integrate, rho cubed over 3. Do y'all follow me? So I get rho cubed over 3. And that would be the total current inside a radius rho. That's equal to 2 pi rho h phi. One of the things you can see is the 2 pi go, right? And therefore you get an h field in the phi direction equal to what? K, right? One of those rho's cancels, so it's k rho squared over 3. And that units that would be amps per meter would be in the A phi direction if you wanted to keep track of everything. Everybody with me? Just show of hands. Somebody say what I've done. By the way, that's kind of a classic problem. What you do is make a current density vary as a function of only radial distance. And then figure out the H field first. That's a classic Ampere's law problem. And then after that, you can ask about the energy density, total energy, and then inductance. So after that, what is the magnetic energy density? Now again, that's density. Does anybody remember? Who does? Anybody? How many remember? I don't care if you say it, I'm not gonna call it. You remember? Nobody else. It's very important. Very important. That's equal to what? 1/2. And this is the way I like to write, mu times magnitude of h squared. Now, in the book, technically what it is, would be 1/2, and it would be h dot b. I'm only going to make one comment about this. B is mu h, so it becomes mu times h squared. But this is well beyond the scope of this course. The permittivity, the actual value of mu here, if you had B equal mu h, could be a tensor. It means it's a 3x3 matrix. And then it wouldn't be just mu times magnitude of h squared. You would have to do the full dot product, mu times h. And that's something that happens for very special cases. Like, for instance, in the ionosphere where you have tensor permittivities, tensor permeabilities, which is because of the ionization. That's the topic well beyond the scope of this class. This is standard. Go with me, class? So if we look at this, what is the magnetic energy density? The units of this would be joules, right, per meter cubed, correct? Energy is joules per meter cubed in the MKS system, because it's a density. So what would it be? It's 1/2 mu, whatever. What is mu for this one? Does he give you, is it just mu now? Can you tell me?
He doesn't. This.
We'll assume mu naught. Unless he specifies otherwise, we assume mu naught, okay? So it's 1/2 mu, and what is h squared? Well, it would be what? K squared, right? Over 9, and then it's going to be rho to the 4th. You all agree with that, class? With me? What I'm going to do at this point, I can see all this as a single constant as well. Anybody follow me on that? I'll just circle it, and I'll say I'll make this constant something else. I'll call that C, and just call it C. Just because I want to make sure there's not a problem. Did you have a question? You guys have a question? Anybody? If you can't read my writing.
What are the last two? What is under K and to the
What's under what?
K squared?
It's K squared over 9 because if you look at this, this is 3 here. 3 squared is 9. That's the only reason I did that. I could have left it as 3 squared if you like.
Also, what is to the right?
This,
Yes, sir.
rho to the 4th. Because that's rho squared, this would be rho to the 4th. Only thing I'm doing is taking this and squaring it, multiplying it by 1/2 mu. That's it. So this would be rho to the 4th power. Does everybody agree with this, by the way? Right? I'm just going methodically through. Now you have to know energy density, magnetic energy density, and electrostatic energy density. While I'm at it, because you're going to get this over and over again. What is the electrostatic energy density? Does anybody remember? It's 1/2, it's D dot E, or 1/2 epsilon times E squared. And that would be the electrostatic energy density, like inside a capacitor. Y'all with me? That's the magnetic energy density. So if I have that, the next thing I need to do is integrate that energy density over the volume. He asked for the what? Internal inductance per meter in that one, correct?
Per unit.
All right, with me or per unit length. So now we do that, and I'll do it right here. I think you see this. This is a pretty good problem. So what is it going to be? I made that all C, so just for everybody's sake. This is really a constant C times rho to the 4th. Agreed? Now we go ahead and we get the total energy. And the total magnetic energy would be what? The integral of the magnetic energy density over the volume, correct? And I'm just putting it here so you know the next step, what I'm going to do. Do y'all agree with this? All right, so the total magnetic energy would be, it's a double integral. Actually, it's a triple integral. It's per meter, so you really don't need the last one. But you follow me on this? So I put the energy density down, which is C times rho to the 4th, right? Now, what's the differential unit of volume in cylindrical coordinates? N times dz, exactly. So it's going to be d rho, then it's going to be rho d phi, then it's going to be dz. Y'all agree with that? I want to make sure everybody sees this. Right? How many see this right? Now, that integration, we have to put the limits. Where does rho go from? I said the radius was a, probably gives you a value. What is the value? Just a, or does he give you an actual value?
So he doesn't give you a value.
What's that?
He doesn't give you a value.
All right, good. It's a. So rho goes from 0 to a, right? Where does phi go from, class? 0 to 2 pi. And z? 0 to 1. This would be the actual definition of that, right? So I'm going to do something. Oh, I'm at this. That magnetic energy density is equal to 1/2 Li squared, right? We still need I, don't we? I didn't calculate I, did I? We're going to get that in a second, but does everybody follow me? Why don't I set up the I integral too? I'll do it over here. So I actually had it right there. So to get the total current I, that would be a double integral as well, correct? Of the current density, remember the current density was K rho, K was 40,000. So it would be K times rho, oops, K, 4. It would be K times rho, and that's actually in the A rho direction, dot, and the differential would be what? D rho times rho d phi. And it's in the A rho direction. I'm trying to just show you this formally. That's what you would see if you looked in a textbook or in a journal paper. Something of that. They'd have the vector sensitive. Y'all with me? Now when you do this, where does rho go from in this case? If we want total current from 0 to A, right? The radius, just A. Where does phi go from, class? 0 to phi. 0 to 2 pi, right? Y'all with me on this? I'm trying to help you. 0 to 2 pi. All right, so what is I? That goes away. What do you get? K comes out in front. You get the 2 pi right off the bat. Then I have rho times rho, which is rho squared d rho, which would be integrate rho cubed over 3. Put in 8, it's a cubed over 3. Y'all with me, everyone? All right. Now, let's execute this integration. What do you see happening for total energy? Well, how about the dz? I mean, the dz goes from dz integrated to z from 0 to 1 is 1, right? So we don't even bother with that. What about the next one? d phi goes from 0 to 2 pi. Just bring out a 2 pi. What about the next thing? I better bring out the c or I'll forget about it. Right? Then you got rho to the 4th times rho to the 5th, correct? Integrate that, you get rho to the 6th, right? Over 6 from 0 to a, it's going to be a to the 6th all over 6. That's the total magnetic energy density. Do y'all agree with this, class? And then you get what? That's equal to 1/2 L, and what's I? That is K times 2 pi A cubed over 3. Hopefully y'all follow me on what I'm doing. You agree with this, class? Now, I mean, if I'm doing this, and I mean I'm working on a paper, not the board, I cross out things. On the board, I erase things. Does everybody see the 2 pi's on both sides? Right? So I'm going to eliminate that. Does everybody have this before I just start doing it? I'll wait a second. Go ahead.
The I on the right side is squared, correct?
Pardon?
On
Yes, I'm sorry. I didn't put the square down. I'm sorry, you're right. My bad. All right, so in that case, I'm glad you said it because the 2 pi is going to survive, I think. Right? All right, let's see what happens. I'm sorry about that. Everybody with me? So when I do this, I guess what I'm going to do, try to find this easiest one. Let's see. You can help me if you want. When I look at this, I'm going to have, I can write this down as k squared 2 pi squared a to the 6 over 9. And that takes care of squaring that out there. So I'm going to erase this so I have something to look at. Y'all with me? I'm just trying to get down to a squared function. I think everybody agrees the a to the 6 I can erase. Do you agree with that, class? All right, so I'm going. Now, the next thing I can see is 1, 2 pi on this side and that side can be removed. So I can erase that. And erase that squaring. Right? Now after that, take a look at this. I guess I can multiply both sides by, let's just erase the 2 here. Right? I hope everybody follows me on this. I'm just trying to get it down to something that's solvable easily. Then invert the pi over 9 and the k squared. So now I have 9 over pi divided by 1 over k squared. And that should be the internal inductance. There's my C. I'm trying to see if there's a quick way. So let me see if I can do this. That's going to be equal to 1 over k squared. And we have 9 over pi right here. And then I have that divided by 6, and then C, and C is equal to 1/2 mu k squared over 9. Let's see what happens. Y'all with me? Let's see if that works. I think everybody sees the k squareds go away. You good with that, everyone? I don't want to go too. Do you follow me on this one? Everybody? Far back? You guys got it? All right. So I'm going to get rid of the k squared. Y'all agree the 9s go? And I guess we could reduce it more because mu would be mu 0 is 4 pi times 10 to the minus 7. But at this point, what is this really going to be? This is 1 over 12 pi mu. And if it's mu 0, it's just mu 0. Is that what he has? I don't know. The answer? Anyone? Is that it? Jonathan? Is that right? Okay. No, but you see the idea behind this. If you're given a density, current density, and you're looking for inductance, then get the magnetic energy density, right, by getting the H field next. So it's J gives you H gives you the magnetic energy density. Have to integrate the magnetic energy density to find total energy, and equate that for 1/2 Li squared. Follow me on this, class? Now you're going to see this kind of thing. 1/2 Li squared is the energy, or 1/2 CV squared for a capacitor, till doomsday. In your upper level classes, this stuff is just assumed that you know. It's like V equals IR, so you have to get familiar with it. All right, that was that problem. Now the other problem we'll do, maybe we can do that a little quicker. I want to get to magnetic circuits. Do you know, can you get this kind of eraser at the bookstore? I would love to have this in other classes. This thing is nice. All right. What was the next problem is what? 58, right? All right. Give me the specifics for that problem. Anyone? This is what, 458? Go ahead. I'll use that blue marker.
It's a pair of concentric conductor loops.
Go ahead, read the whole thing. One is inside the other?
Yeah, centered in the same plane, with radii A and B.
All right, let me show you this. This is one of these problems. It's a little tricky. There's an assumption there. So they have two loops, and I'm looking right down the z-axis of this one. And they got one loop. I'm going to call that, is it radius A below? And then they have another one out here, B. You all with me? Now, the assumption is this, that A is much less than B. That is an important assumption. Does everybody follow me on this? With me? So he wants the mutual inductance between the two. That's what he asked for, isn't it? All right, for this one, because of this, we can assume that the B field or H field in this region is about constant. Y'all with me? So if we can find the H field or B field at the origin, and it would be coming out of the board, then we can find that's just assumed as a constant. If we multiply that by the area of the loop, we would have the flux. Does everybody follow me? The other assumption is you have to define a current. So we assume a current is here, and I'm going to assume the current is this way, I, in this direction. Now, back in the day when we did this, remember I said if you have a loop like so, of a radius A with a current I, and you wanted the H field on the z-axis at any height, you don't have to write this down, but I'm just refreshing your memory. This was equal to 1/2, and then it comes out to be, it's 1/2. Down here, it's going to be the height. If you wanted it here, I'm trying to just write this down here so it brings back memories. And we had a differential link. Normally we had a DI here causing this differential H field. After you do the whole 9 yards and do the integration, you find this. And it's going to be this over really the radius A squared plus Z squared to the 3/2 power. And then on top, what you end up with is getting A squared, and it's going to be times the current I, and it's in the AZ direction. I think that's the form he has in his book. Doesn't it, class? Can you check on that? This would be for, there's different ways to write this, but I think he has, it's A squared over 2A squared plus E squared to the 3/2. Am I right? No? I'm pretty sure. Can anybody just take a look at it? Jonathan, can you take? I don't know where it is in the text, but I'm just trying to, I want to give you a marker point so you know where I'm getting this. I want to know the equation of it possible. This would be H field from a loop. It's one of the very first problems after he talks about the differential valuation. Okay, see it? All right, what equation? 4.9 on page 218. Now, here's the deal. What's the value of Z right at the origin? 0. Actually, what I'm trying to do is I'm showing the Z-axis coming out of the board, and we're assuming these two loops are in the XY plane. Z equals 0. So I have to get the H field at Z equals 0. What is the H field at Z equals 0 then? It's going to be what? 1/2 I, right? Now what happens here? When Z is 0, I have A squared over A cubed. Do y'all see that? Or I have simply 1 over A, huh? So it's divided by A. And that's going to actually be the H field right here. It's going to be coming out of the board. Right? So I've got the H field, therefore what's the B field going to be? Mu times H, right? Or it's going to be mu, in this case mu 0 if it's air, times I over 2A. And that would be Webers per meter squared. That would be the H field coming out of the board. How many see this right here? I just took B field. I took the B field, multiplied it by mu to get the H field. You all see this, class? Now, how much flux goes through this region right here? Remember, my assumption is the H field does not vary over the area of that small loop. That's the assumption. Y'all follow me, class? You asked me about this. Are you with me so far? All right, so the total flux, magnetic flux, it would be here, would just be the area of the loop times the B field. What's the area of that inner loop? Anyway, what's the area of something of radius A? Cross section. Pi A squared, right? Make sure you know this. I'm trying to make sure you know. You have to know these. So it's going to be pi A squared times the B field, which is mu 0 I over 2A. Now that's the magnetic flux. What is magnetic flux in terms of inductance? I times the mutual inductance is the magnetic flux, isn't it, class? So if you just take that, the magnetic flux, and set it equal to I times, and I'll call it Lm, it's mutual, you can see that the mutual inductance is simply the magnetic flux divided by the current. Well, you just erase the current. So you get this equal to really pi A over 2 mu 0, and that would be Henry's. And that's a mutual inductance. Does that agree with the answer in the text? I don't know, but I hope it does. Anybody confirm that? Yes? No? Anybody? Let's look.
I think the A is squared. A squared over 2.
That should be over 2A, so the A squared on top would cancel one.
In this case, B radius here.
Oh, you're right. It should be the outer. That's my problem. I'm so sorry about that. I got casual. This should be B. Right there. And that should be B. I'm so sorry. So this should be B. Yes. And that means this would be, that's still pi A squared there, but this should be B. And that means this should be A squared over B here. I'm sorry. You're right. Thank you for catching that. That was not intentional. I got a casualty. Are you with me, class? And that should be the right answer. Now, I'll tell you, these problems, I mean, in the real world, a lot of these things are going to be based on some assumptions. Now I have some questions for you. What do you think would happen if I didn't have one loop here, but I had two loops on the outer part? Anyway. It would be 2 times that. What if I had n number of turns on the outer one, closely spaced? Class? The inductance would go up, the mutual by n, right? Y'all hear me? Now, second question. You know it's proportional to n on the outer one because the flux would keep increasing by the number. What about on the inner, this inner one? What happens if it's not 1 turn, but m turns, or L turns? What happens? They multiply by L. Y'all follow me? So it's the total. Yes.
So it's a scalar property? Like
Well,
more loops,
yes, it's proportional. It's a linear property. So whatever happens if I have 10 turns on the inside and 50 on the outside, it would be 50 times 10 would be the magnifying power of those numbers. Y'all follow me, class? Trying to give you some hints on how to solve these. Everybody see this? What don't you see? You're looking at me suspicious. I'm not trying to pull the wool over your eyes. I'm just trying to help you understand this. Remember this. So I do this kind of stuff all the time. I'll give you a problem, something like this. And what I might do is take this, and instead of putting it this way, I might do something really diabolical. Suppose I take this and I put 5 turns, all right? And I put this at a radius B. And then I take something where I take the B field, I make another smaller loop, but I don't put it at the origin. I displace this by, say, a height of, if this is a radius B, make this 1/50 B. In other words, a very small distance away from the origin. Y'all follow me, class? Now, this has a radius A, and it has, let's see, all right, I said 5 turns there. Make this 100 turns on the other one. Y'all follow? Now I want the mutual inductance between those two. The same process, right? First, you're going to assume that the magnetic field over this, because it's just slightly above the origin, right, is going to be about the same as the origin. Y'all follow? I'm sorry, it's the same across the cross section. Let me finish my thought. Y'all with me? Now that means if I want the total flux through there, I'm going to multiply whatever the flux or whatever the B field is that's normal. Can't have an offset, right? The normal B field, which you can get from that equation, because you'll notice that's in the Z direction. Y'all follow me? But now you would have to include Z. It's not 0. Y'all follow me? Then, once you found that H field, you'd multiply it by, right, by the area to get the flux. But really, the thing about it is, the way to do this problem is, forget the number of turns. There's 1 turn on the outer, 1 turn on the smaller. Find the flux from the 1 turn on the outer through this one by calculating the H field right there at this point, multiplying by the area. Y'all with me? Then do the magnification. Multiply by the number of turns in the outer loop times the number of turns on the inner loop. Y'all follow me? And that will give you the mutual inductance. But there's an assumption that the flux is constant over that cross section. Can you all follow me? Or the B field's constant. How many understand? Are you with me? Do you understand? Guys? Over here? You guys got it? So I'm trying to show you this. That's a very, very common thing that I mean, people ask you all the time. You have to be aware of this. Now, is there another question before I go to magnetic circuits? Magnetic circuits will help you with inductance calculations immeasurably. So I'm going to do this. Now we do magnetic circuits. Did you guys understand this right here? This is a good problem. All right, now we're talking about magnetic circuits. This is the last section, I think, in that chapter. All right, and what we do is build an analog or a model that exactly has an exact dual with your electrical circuits. So here we go. First, with magnetic circuits, and I'll give you the typical magnetic circuit. They're going to have a bar like this of iron. They'll have a core like this, as such. And this bar will have a total length. If I went around, this thing this way, I'm trying to show you this thing. It would have a total length L, actually. Let me reduce, you get the idea, it's a 3D picture there, but I'm just going to do this. I'm going to assume we can look at this from a 2D perspective. So we're going to have something like this, and we're going to go ahead and put turns on this. And we're going to have a current I flowing in it. I'm just showing you the problem. And we're assuming this has a certain cross-sectional area. A, and it has a certain permeability, mu relative. Now, mu relative generally is much greater than 1. Follow with me? What that means is all the magnetic flux we're talking about is assumed contained within them. There's no field fringing we have to worry about outside that area. Now we build the door for this. So what actually happens is, if you have a voltage here, Vs, it will cause this current. You don't need to worry any more than that, all right? Now, what we say is this current and the number of turns, and I'll just call it N here, is something, it's called a magnetomotive force. It's like an electromotive force or a voltage. So the magnetic circuit looks like this. You just put a voltage source here, equivalent voltage source, that has a strength Ni. This is called the MMF, magnetomotive force. And over here is our electrical and analog. So you know that's just like a voltage. You're familiar with voltage. Now, the next thing you take a look at is, we're going to assume this has a certain total length around here, L. All right? And think back when you did resistance. If you had anything with a cross-sectional area A, length L, and conductivity sigma, the actual resistance between the ends of this would be proportional length, inversely proportional to area, and inversely proportional to sigma. That would be an ohms. Do you remember that? How many did? Remember resistance is proportional to the length if it's constant cross-section, inversely proportional to cross-sectional area, and it's inversely proportional to sigma. Do you all remember this class? It's very important you do. You'll see this again on the final. So here, we're going to have a magnetic resistance, or it's called a reluctance. And the magnetic reluctance, he uses a script M, is proportional to the total length, path length around here, and it's inversely proportional to the area, cross-sectional area that the magnetic flux is flowing through, and it's inversely proportional to mu. Now, I've showed you that, but I'm going to just show you that now this looks like a resistor R, which has a value of L over sigma A. I think he shows this exact relationship in his book. Now think back here to the electrical analog. If you have this, you could find the current I, couldn't you? That would be what? The voltage divided by the resistance. That's simple. Do you all agree with that? So this is going to be whatever this voltage is right here, divided by the resistance. I don't need to put all the variables in there. We're going to leave it like that, right? Over here, instead of current, you get flux in Webers. So the magnetic flux flowing here would be Ni divided by the magnetic reluctance. What page is this in the book, by the way? I think you're on. Whatever. 271. It's probably 271, 272. You have this. It's really important to see. Y'all with me? Take a look. Now, that's the flux, right? The units of flux are Webers, right? What if you wanted the B field anywhere in here, assuming it's constant cross-section? If you wanted the B field, how would you get it? Well, what is B field? What are the units of B field? Anybody? Webers per meter squared, right? We have Webers. We can get that by dividing by the cross-sectional area that the flux is through, which is assuming it's uniformly distributed across that cross-section. So from here, we can get the B field. I'll put that here. The B field is the magnetic flux divided by the cross-sectional area, and I can leave it like that, or I could put Ni over the reluctance divided by the area. Now that would be in Webers per meter squared. That B field is like the current density over here. So the current density that would be flowing in this circuit, if it was a 3D circuit, J would really be I over the cross-sectional area. Does everybody follow me on this? I'm going to see this right here, the parallels. He has these in the book. Turn the page. He'll have maybe the next page. Maybe the next page. He has it somewhere in there. I don't know. Maybe I don't see it. Anyway, he'll have this drawn up, I promise you, in that section if you read it. Y'all with me? Now, so far I've got all this. Once I have the B field right here, how do you get the H field, class? Right? Just take that B field. I'm about out of time. Take the B field and divide by mu, and now I have the H field. The H field, remember, we got the similar thing we got was J, right? If you divide J by sigma, you get the E field, right? So if you want the E field, you take J over sigma. It's the same exact analog to what we're doing here. The H field is like the E field. The E field is in volts per meter, correct? This is in amps per meter. Amps instead of volts, the magnetic analog. Y'all with me? Now finally, after that, if I wanted the inductance, I'm going to throw this out here. Who can tell me how you would get the inductance of this system? What is inductance in terms of flux? It's what? The flux flowing through a single turn, do you all remember that? Divided by the current causing. But if you had more than one turn, you would have to multiply by the number of turns. Do y'all follow me? So the inductance of that system in that ball would be equal to the number of turns in, because the flux flows through each one of those turns, times the magnetic flux, which is over there, and then you have to divide it by the current causing it. And this is a real easy way to get inductance for any system that concentrates flux that is caused by turns. It doesn't matter if it's a toroid, if it's a bar like that, or anything else. We'll talk more next time about this, and I'll give you a promise. Does everybody understand that? All right, have a great weekend. How many are going to the game? I sure hope